Welcome to our latest video on the topic of reactions of primary amines with nitrous nitric 3 acid. This video is suitable for A-level students. By the end of this video lesson, you should be able to describe the reactions of primary aromatic amines with cold nitrous nitric 3 acid and the different reactions that take place with primary aliphatic amines. You should also be able to describe and explain the coupling of benzenediazonium salts with phenols and aromatic amines. And finally, you should understand the meaning of the term chromophore, be able to identify this group in an azo dye, and be able to explain the origin of colour in these dyes in terms of the wavelengths of visible light absorbed. Now, in our previous videos on amines, we've learnt that amines are nitrogen compounds in which one or more of the hydrogen atoms in ammonia, NH3, is replaced by alkyl or aryl groups, and the number of alkyl groups determines whether the compound is a primary amine, a secondary amine, or a tertiary amine. So if we have a primary amine, one of the hydrogens in ammonia has been replaced by an alkyl group or an aryl group. If we have a secondary amine, two of the hydrogens in ammonia have been replaced by alkyl or aryl groups. And if we have a tertiary amine, all three of the hydrogens in ammonia have been replaced by alkyl or aryl groups. Now, in our previous videos on amines, we've looked at the chemical reactions that amines have. We first looked at the reactions of amines with acids, such as hydrochloric acid, and the fact that all amines are bases and will react with acids to give soluble salts. We've learnt that amines react with acids and produce heat, therefore an exothermic reaction takes place, and their fishy smell is lost when it forms a salt. For example, methylamine and hydrochloric acid make the salt methylammonium chloride. In our last video, we learnt that primary amines undergo ethynylation reactions, and this involves the primary amine being reacted with ethanol chloride and the hydrogen atom in an amine being replaced by an ethanol group, a CH3 bonded to a C double bond O. And the result is a formation of a compound called a substituted amide. Now, in this video, we're going to look at the reactions of both primary aliphatic and primary aromatic amines with nitrous acid. Now, nitrous acid is HNO2, and it's often referred to as nitric 3 acid because the oxidation state of nitrogen in nitrous acid is +3. Now, the nitric acid that you've come across previously is HNO3, and that is referred to as nitric 5 acid because the oxidation state on the nitrogen is +5. Now, nitrous acid is very unstable, and therefore it has to be made in situ by reacting sodium nitrite, NaNO2, with dilute hydrochloric acid. So NaNO2 plus HCl makes HNO2 plus NaCl. Now, primary amines react with nitrous acid in a number of different ways depending on whether they are aromatic, aliphatic, and the reaction conditions involved. So now let's look at these different reactions. So primary aliphatic amines, compounds such as methylamine, ethylamine, propylamine, butylamine, they will react with nitrous acid at any temperature to give an alcohol, water, and nitrogen gas. And when this reaction takes place, because you're making nitrogen gas, you will observe fizzing. Now, primary aromatic amines, such as phenylamine, will give a similar reaction at room temperature, as long as the temperature is above 10 degrees C. So here I have C6H5NH2, which is phenylamine, plus nitrous acid, HNO2, and that will form phenol, C6H5OH, plus water, plus N2 nitrogen. And once again, I will observe fission because I produce nitrogen gas. Now a different reaction takes place if you have a primary aromatic amine such as phenylamine and you react it with cold nitrous acid. That is nitrous acid between around 0 to 10 degrees C, preferably between 0 and 5 degrees C. In this case, the primary aromatic amine will react with the nitrous acid to form a new compound called a diazonium salt. So this equation shows what takes place. So C6H5NH2 is phenylamine, and it will react with nitrous acid, HNO2. It will also react with any hydrochloric acid that's present, and that was, remember, present to form the HNO2. And that will form C6H5N, triple bond N, with a positive charge on the first nitrogen, and a Cl- ion, which is a counter ion, and 2 water molecules. Now this compound is called benzenediazonium chloride. And this compound is important in synthesis, and it's also important because it's used to make coloured dyes called azo dyes. Now when this reaction takes place, the nitrogen remains on the aromatic molecule. So therefore you observe no fission. And this is a way of distinguishing between an aromatic primary amine and an aliphatic primary amine. Because if you add cold nitrous acid to both, the aliphatic primary amine will produce nitrogen gas and fission, and the aromatic primary amine will produce the diazonium salt, and you'll observe no fission. Now the reaction of a primary aromatic amine with cold nitrous acid to produce a diazonium salt is called a diazotization reaction. So now let's look a little more closely at the diazonium salt. So if we react phenylamine with cold nitrous acid, and the nitrous acid is made from sodium nitrite and dilute hydrochloric acid, the diazonium salt that we'll make is called benzenediazonium chloride, and it has the following structure, which can be seen on this slide. And it's important in synthesis because we've made an electrophilic form of benzene, and this means that this form of benzene will react with nucleophiles. Now you remember when we studied aromatic chemistry that benzene reacts with electrophiles. So this opens up lots of synthesis reactions and different pathways that we can't do normally, because suddenly we've got a form of benzene that reacts with nucleophiles instead of electrophiles because of this positive charge on the N triple bond N. Now, as I mentioned previously, we can use this reaction with cold nitrous acid to help us distinguish between a primary aliphatic amine and a primary aromatic amine. Because with cold nitrous acid between 0 and 10 degrees C, and preferably between 0 and 5 degrees C, the primary aliphatic amine will produce an alcohol, water and nitrogen gas, and will observe fission, and the primary aromatic amine will produce this diazonium salt and will observe no fission. Now, if when making the nitrous acid we use dilute sulfuric acid instead of dilute hydrochloric acid, the diazonium salt that will be formed will be called benzene diazonium hydrogen sulfate instead of benzene diazonium chloride, and it will have the following structure. So you can see from this slide that we have a benzene ring attached to an N2 with a triple bond between the two ends and a positive charge on the first nitrogen, and the counter ion is a hydrogen sulfide ion, which is HSO4 1-. Now benzene diazonium salts are very unstable, And this is because this N2 group can be replaced by a hydroxyl group simply by warming the diazonium salt in water. So if the temperature goes above 10 degrees C with benzene diazonium chloride, the nitrogen comes off the molecule. We get an alcohol, so C6H5OH, which is phenol. We get nitrogen and we get HCl. Now, as I mentioned previously, one of the major reasons why diazonium salts are important is that this is a form of benzene that will react with nucleophiles because there's a positive charge on the nitrogen attached to the benzene ring. And we've learned previously when we studied aromatic chemistry that benzene normally reacts with electrophiles. So we're able to carry out reactions that we wouldn't be able to do normally because we have a form of benzene that reacts with nucleophiles. So for example, iodobenzene is formed when benzene diazonium chloride is warmed with aqueous potassium iodide. So you can see here we've got benzene diazonium chloride plus potassium iodide, and we get C6H5I, which is iodobenzene, plus potassium chloride and nitrogen gas. Now in this reaction, the iodide ion is a nucleophile and it reacts with the diazonium salt, which is acting as an electrophile. Now, diazonium salts are of considerable commercial value as they can be used to make azo dyes, and this is a group of dyes that is widely used to colour food or other substances. So now let's look at how we make azo dyes. Now, an azo dye can be made by reacting a diazonium salt with an alkaline solution of a phenol. So this is a benzene ring with an OH group, and this is usually obtained by using sodium hydroxide. Now, benzene diazonium chloride, C6H5N2 plus Cl- readily couples with phenol in alkaline solution to produce an azo dye. And this azo dye is called 4-phenyl-azophenol according to the following equation. So you can see that I've got my benzene diazonium chloride, and what happens is that the triple bond between the two nitrogens breaks, and this changes to a double bond, and then a bond forms to link the nitrogen to the phenol. So my other products are sodium chloride and water. Now this compound is a yellow-orange dye, and azo dyes tend to be red, yellow or orange, and it's called an azo dye, and it contains this azo group, which is a single bond to a nitrogen and then a double bond to a nitrogen and then a single bond. Now it's this azo group in an azo dye which is responsible for absorbing light in the visible region and causing its colour. And this group is called a chromophore. Now the reason that NaOH is needed is because benzene diazonium chloride is a positive form of benzene. It's an electrophilic form of benzene. So we need to make a nucleophilic form of phenol for phenol to react. So therefore, when I have NaOH, the H comes off the phenol to make an O- ion, and that's why it reacts with benzene diazonium chloride. Now this reaction that takes place is called a coupling reaction, and when benzene diazonium chloride couples with phenol, it couples or joins in the 4 position. Now the OH is on carbon 1 of phenol, and 3 carbons along is the 4 position, and that is opposite the OH, and that's where the benzene diazonium chloride couples to the phenol molecule. It joins opposite the OH group. Now here's another example of an azo dye formed when benzene diazonium chloride reacts with a phenol. Now in this case, it's a phenol that has 2 benzene rings in it, and it's called naphthalene 2-ol. So if we react naphthalene 2-ol with benzene diazonium chloride in the presence of aqueous alkali such as NaOH, we form a red azo dye, and this is called 1-phenyl-azo-naphthalene 2-ol, and it's also called Sudan 1, and it's a red dye that used to be used to colour curry powder but is now banned in the UK. Now once again, when benzene diazonium chloride couples with this phenol, naphthalene 2-ol, the triple bond between the nitrogen breaks to form a double bond, and a bond forms between the nitrogen and the naphthalene 2-ol. And this time it couples next to the OH group because the 4 position is taken by the ring, so it has to couple next to the OH group. And this is common in these circumstances. Now this azo dye is red, and once again this red colour is caused by the presence of an azo group which is absorbing light in the visible region. Now it's also possible to have coupling reactions between benzene diazonium chloride and aromatic amines. And once again you form an azo dye with this azo group. So here we have benzene diazonium chloride and the aromatic amine phenylamine. A coupling reaction takes place and the triple bond between the nitrogen breaks to form a double bond, and a bond forms between the nitrogen and the phenylamine. Now this azo dye that's produced is a yellow azo dye. Now azo dyes are coloured compounds because they contain a chromophore. Now a chromophore is a structural unit in a molecule that is responsible for the absorption of radiation of a certain wavelength, generally in the visible or ultraviolet region. Now if the absorption takes place in the visible region, the colour that's not absorbed is the colour observed. Now the chromophore in these azo dyes shown here is the azo group, which is a single bond to a nitrogen, a double bond between the two nitrogens, and then a single bond. Now this group is often referred to as being conjugated. A conjugated system of electrons is what exists when you have a single, double, single bond. Now conjugated systems of electrons make good chromophores. Now the first azo dye here has a maximum absorption at 384 nanometers. So it's absorbing in the blue end of the spectrum, and that's why the colour you see is the colour not absorbed, and in this case is yellow. Now the second azo dye here, which is formed from benzene diazonium chloride and naphthalene 2-ol, absorbs at a slightly different wavelength, but it's still absorbing in the blue end of the spectrum, and that's why it's red/orange. Now you have to remember that the colour that you see is the colour not absorbed. So therefore you're seeing an orange-red dye because it's not absorbing orange and red, and it's absorbing light from the blue end of the spectrum. Now the reason that these have a maximum absorption at slightly different wavelengths is because the azo group is attached to different groups of atoms, and this affects the wavelength that the absorption occurs at. So now let's test your understanding of this topic with some practice questions. So here's the first practice question. Read through the question, pause the video, have a go at it, and then we'll go for the answer. So this first practice question is asking you to state the reagents necessary to produce the diazonium compound from the acid. So the reagents needed to produce the diazonium compound would be nitrous acid. You could just say nitrous acid or put the formula HNO2, or you could write down the actual reagents used to make nitrous acid, which would be sodium nitrite, NaNO2, and a hydrochloric acid. 1 mark for that. So here's the second part of this question. Read through the question, pause the video, have a go at it, and then we'll go for the answer. So this question is asking you to draw the structure of the amine that would react with benzene diazonium chloride to form the azodimethyl red. So this amine would be a benzene ring bonded to a nitrogen with 2 CH3 groups attached. So if you drew that correctly, there is 1 mark for that question. So here's our next practice question. Once again, read through the question, pause the video, have a go at it, and then we'll go for the answers. So the first part of this question is asking you to explain why methyl red is a coloured compound. So as you said, the molecule contains a chromophore group, a single bond to a nitrogen, a double bond to a nitrogen, and then a single bond. This is sometimes referred to as an azo group. There's 1 mark for that. And if you said that this absorbs radiation of a certain wavelength in the visible region, that would get you the 2nd mark. So part 4 is asking you to draw the structure of the ion produced when methyl red is present in aqueous sodium hydroxide. So what we've got to do here is look at the structure of methyl red and see if there's any group on this molecule that would react with alkali. Is there any acidic group? And there's a COOH. So that would act as an acid and it would lose H plus to form a COO minus ion. So to get this mark, all you'd have to do is draw out the structure showing the COOH changing to COO minus. So here's our next practice question. Once again, read through the question, pause the video, have a go at it, and then we'll go for the answers. Now this question is asking you to give the displayed formulae of the 2 starting compounds that react via a diazonium compound to give this dye mordant orange 1. Now the key words here are via a diazonium compound. So they don't want you to draw the diazonium salt, they want you to draw the compound that makes the diazonium salt. So the compound I would need to form the diazonium salt would be a benzene ring with an NH2 group on, and then opposite the NH2 group would be an NO2 group, and that would be the compound that would form the diazonium salt needed to make this dye. Now the other compound I need would be a benzene ring with a carboxylic acid group and an OH group next to each other, and those 2 compounds would join together in a coupling reaction to form the dye mordant orange 1. So this question is worth 2 marks, so there's 1 mark for each correctly drawn compound. So here's our final practice question. Once again, read through the question, pause the video, have a go at it, and then we'll go for the answers. So this question says, describe the reaction of a primary aliphatic amine such as butylamine with nitrous acid, and it's asking you to compare this reaction with the corresponding reaction of a primary aromatic amine with nitrous acid, and then state how the product of the latter reaction can be used to make azo dyes. In both cases, your answer should describe what is seen as well as any essential conditions. The formulae of the products are not required. So if you said butylamine, the primary aliphatic amine, reacts with cold nitrous acid, giving bubbles or fizzing, that gets you 1 mark. And if you then said that with cold nitrous acid, so they've quoted on this mark scheme 5 to 10 degrees C, but you could write down 0 to 10 degrees C or 0 to 5 degrees C, as long as you state that it's cold, you would say that this produces a diazonium compound. So there's 1 mark for the temperature and 1 mark for the idea of a primary aromatic amine producing a diazonium compound. Now, if you then went on to say that this diazonium compound, or diazonium salt, or benzene diazonium chloride, goes on to react with phenol or naphthalene 2-ol, or even an aromatic amine, and this normally takes place in alkaline solution to produce an azo dye, which is red, yellow, or orange, you get the remaining marks. So 1 mark for the idea that it would react with a compound such as phenol or naphthalene 2-ol or an aromatic amine, and half a mark if you said alkaline conditions, and half a mark for the idea of it producing a red, yellow, or orange dye. So this question is out of 5 marks. So there's 5 marks if you said all those points. So that concludes this video lesson. So after watching this video, you should now be able to describe the reactions of primary aromatic amines with cold nitrous nitric 3 acid and the different reactions that take place with primary aliphatic amines. You should also be able to describe and explain the coupling of benzene diazonium salts with phenols and aromatic amines. And finally, you should understand the meaning of the term chromophore, be able to identify this group in an azo dye, and be able to explain the origin of colour in these dyes in terms of the wavelengths of visible light absorbed. So that concludes this video lesson. So please check out our YouTube channel, Dr. O Chemistry, which has lots of GCSE, AS and A-level videos, and our Twitter site @RadaChemistry.